Welcome to the Eternon channel. This is a place for gentle science-based stories about Earth and its past, created for learning relaxation and sleep. If you find it helpful, please like and subscribe to support the channel. Now take a breath and begin. Far from the warmth and brightness of the inner solar system, the region where sunlight thins and planets become small points is quiet and sparse. This outer neighborhood is defined less by solid boundaries than by distance and motion. It stretches beyond the orbit of Neptune past the scattered disk of icy remnants and into the broad domain where the sun's gravity still holds, but weakly. Here time moves slowly in human terms, and change is measured across many thousands or millions of years. Small bodies drift through this space on long paths, shaped by ancient events, such as the formation of the planets, or close passes by other stars, when the sun was young and still part of a dense stellar cluster. Most material in this distant region consists of ice mixed with dust and rock. Water ice dominates closer in, while farther out, the cold allows more volatile substances, such as carbon monoxide and carbon dioxide ice, to remain solid. These bodies preserve early conditions from the birth of the solar system, because they have spent most of their existence far from heating and collision. Their motions are governed mainly by gravity following predictable arcs that can be traced backward and forward using established physical laws. When one of these objects begins to fall inward, drawn slowly toward the sun, its path usually reflects the cumulative pull of the planets and the star itself without sudden changes. The solar system does not exist in isolation. The space between stars contains dust gas and occasional interstellar objects that pass through each carrying a history from another system. When such a visitor enters the sun's gravitational influence, it approaches from a direction unrelated to the flattened plane where most planets orbit. Its speed relative to the sun is often higher than that of native objects, and its path is open rather than closed, meaning it will pass through once and not return. These traits allow astronomers to distinguish between long-period comets bound loosely to the sun and true interstellar visitors that originate beyond it. The detection of faint objects at such distances relies on wide-field surveys that repeatedly scan large portions of the sky. These instruments look for points of light that move slightly against the background of distant stars. At first, the movement is subtle. Over nights and weeks, patterns emerge that allow preliminary paths to be calculated. In the outer solar system, uncertainties are large because the object is dim and far away, and small errors in position can translate into large differences in predicted future motion. Careful accumulation of observations is required before any strong claims can be made about an object's origin or behavior. In this region, the sun's gravity is the dominant force, but it is gentle. Objects can be nudged by passing stars or by the collective gravity of the galaxy itself. These influences act over long periods, slowly reshaping distant reservoirs of small bodies. When an object begins its inward journey, it carries with it the imprint of these past interactions. Astronomers expect such an object to follow a smooth curve toward the inner solar system, accelerating gradually as it approaches stronger sunlight and gravity. Deviations from this expectation, especially when detected early and far out, attract careful attention. The object known as 3I/Atlas first appears within this outer context. At the time of its earliest observations, it is still far from the Sun, where heating is minimal and activity is usually low. In this cold environment, native comets typically remain inert, showing little or no visible emission of gas or dust. Their surfaces are frozen, and any volatile material beneath is sealed under layers that have remained unchanged for long spans of time. Because of this, their motion is expected to be almost purely gravitational, following paths that can be predicted accurately once enough measurements are gathered. The outer solar system also imposes limits on what can be known quickly. Light reflected from a small dark body diminishes sharply with distance, making observations noisy. Atmospheric effects on Earth, even when corrected, add further uncertainty. Astronomers compensate by using repeated measurements and by combining data from multiple observatories. The goal at this stage is not to explain behavior, but to establish a reliable track of where the object is and how it is moving through space. Only after this foundation is secure can deeper questions be addressed. In this distant zone, there is no expectation of dramatic change. Temperature differences across the surface of a small body are minor. Rotation, if present, does little more than redistribute faint sunlight. Any gas trapped in ice remains solid. The environment is stable, and stability leads to predictability. This is why the outer solar system serves as a reference point. Motion here reflects origin and initial conditions more than active processes. When an object's path does not match this calm expectation, the discrepancy stands out clearly against the quiet background. The presence of interstellar objects adds another layer of complexity. These bodies arrive with velocities and compositions shaped by other stars and disks. Yet even they, upon entering the outer reaches of the solar system, are expected to obey the same gravitational rules. Their trajectories can be described using the same equations that apply to all masses. Differences in speed or direction are accounted for by initial conditions, not by new physics. This assumption holds unless observations consistently show otherwise. At this stage, nothing is concluded. The outer region is described, measured, and compared against models built from decades of observation and theory. 3I/Atlas exists here first, as a moving point of light, distant and cold, its behavior assessed against a backdrop of expected calm. The groundwork is laid without interpretation. The focus remains on environment, distance, and motion, establishing the baseline against which later changes will be evaluated, all while remaining firmly within the quiet outer reaches of the solar system. The first recognition of 3I/Atlas occurs not as an event, but as a subtle pattern within accumulated data. Wide-field surveys operate by repetition, returning to the same regions of sky night after night. Each image captures countless stars fixed in their positions, and occasionally a faint point that shifts slightly between exposures. In the outer solar system, such movement is slow and easily mistaken for noise unless confirmed across many observations. Automated systems flag candidates, but human review remains essential to separate real objects from artifacts caused by cosmic rays, detector defects, or atmospheric effects. Once a candidate is identified, its positions are measured relative to background stars, whose locations are well known. These measurements form the basis of astrometry, the practice of determining precise positions in the sky. Early astrometry is uncertain by nature. The object is dim, its light spread across a small area of the detector, and the signal competes with background noise. Each data point carries an uncertainty that must be accounted for when estimating motion. At this stage, the goal is modest, to determine whether the object is real and whether it is moving in a way consistent with a distant solar system body. For 3I/Atlas, early detections suggest a slow, steady drift against the star field. The apparent motion is small, consistent with an object far from both Earth and the Sun. Initial calculations produce a rough trajectory enough to predict where the object should appear in subsequent nights. These predictions guide follow-up observations, allowing telescopes to target a small region of sky rather than searching blindly. With each successful recovery, confidence grows that the object is genuine and that its path can be refined. As more data accumulate, the arc of observation lengthens. This arc refers to the span of time over which the object has been observed. A longer arc reduces uncertainty because it constrains the range of possible orbits that fit the data. Early arcs may allow many different paths, some bound to the Sun and others unbound. As the arc extends, incompatible solutions are eliminated. For 3I/Atlas, this process unfolds gradually, with new measurements tightening the possible range of motion. During this phase, astronomers rely on established models of celestial mechanics. These models assume that gravity is the dominant force and that the object behaves as a point mass. The Sun's gravity provides the primary influence, with minor contributions from planets depending on their relative positions. At large distances, planetary effects are small, but they are included for completeness. Using these assumptions, orbital elements are computed. These elements describe the shape, orientation, and size of the path through space. The classification of an object depends on these elements. If the path is closed, the object is bound to the Sun and will return after completing an orbit. If the path is open, the object will pass through once and leave never to return. Early in the tracking of 3I/Atlas, uncertainty allows for both possibilities. The eccentricity, a measure of how stretched the orbit is, hovers near the threshold that separates bound from unbound motion. Small changes in measured position can shift the interpretation from one category to the other. This ambiguity is not unusual at first detection. Many long-period comets appear unbound when observed briefly, only to settle into bound orbits as data improve. Conversely, some interstellar objects initially resemble long-period comets until their high incoming speed becomes clear. For this reason, restraint is standard practice. Astronomers describe provisional solutions and wait for additional observations before making strong claims. The naming of 3I/Atlas follows established conventions. Survey names are attached to objects they discover, and provisional designations reflect the order and time of discovery. At this stage, the name carries no implication about behavior or origin. It is a label used to organize data and coordinate observations across the global astronomical community. Alerts are circulated inviting other observatories to contribute measurements. Independent observations serve a crucial role. Different instruments, locations, and observing conditions provide checks against systematic errors. When multiple observatories report consistent positions, confidence in the measurements increases. For 3I/Atlas, such coordination expands the data set, improving coverage and reducing gaps. The object remains faint, requiring sensitive detectors and careful calibration, but each additional data point sharpens the picture. Throughout this process, attention remains focused on motion, not on physical appearance. At great distances, the object appears point-like with no resolved structure. There is no visible coma, the cloud of gas and dust that often surrounds comets closer to the sun. Brightness measurements are made, but they are interpreted cautiously as variations can result from changing viewing geometry rather than intrinsic change. The emphasis is on building a reliable track. As the orbit is refined, predictions of future positions become more accurate. This allows observers to plan ahead, securing telescope time and ensuring continued coverage. The predicted path extends forward in time tracing, where the object should move across the sky if current assumptions hold. At this stage, the predictions for 3I/Atlas appear reasonable, consistent with a distant object approaching the inner solar system on a long path. Yet even in this early phase, small discrepancies begin to emerge. Residuals, the differences between observed positions and those predicted by the model, are examined closely. Some scatter is expected due to measurement error. Patterns in the residuals, however, can indicate that the model is incomplete. Astronomers monitor these differences, looking for trends rather than isolated outliers. The discipline at this stage is patience. Discovery and initial tracking are about establishing facts, not explanations. The outer solar system provides a controlled environment where assumptions about gravity and inertia are usually sufficient. By carefully documenting positions, times, and uncertainties, astronomers create a foundation that will support later analysis. Any claim about unusual behavior must rest on this foundation, built methodically through observation and calculation. For 3I/Atlas, the initial tracking phase concludes with a growing sense of confidence in the data, paired with an awareness that questions remain open. The object's path is charted with increasing precision, its motion recorded against the fixed stars. Within the quiet expanse far from the sun, the work proceeds steadily, defining where the object is and how it moves, without yet addressing why it moves that way. The motion of small bodies entering the solar system has been studied for centuries, refined through observation and calculation into a set of expectations that guide interpretation. When an object approaches from far beyond the planets, its path is shaped primarily by gravity. The sun dominates, drawing the object inward along a smooth curve. The form of that curve depends on the object's speed and direction before it felt the sun's pull. But once these initial conditions are known, the subsequent motion follows predictable rules. For long-period comets that originate within the solar system, the journey inward often begins in a distant reservoir of icy bodies. These objects approach on elongated paths that bring them close to the sun before carrying them back outward again. Their motion is slow at great distances and accelerates steadily as they fall inward. The increase in speed is continuous and calculable. Changes in direction are gradual, reflecting the steady curvature imposed by gravity rather than abrupt turns. Interstellar visitors follow similar rules once they enter the Sun's domain. Their defining difference lies in their initial speed and direction. Coming from outside, they are not bound to the Sun. Their paths are open, meaning they arrive, pass through, and depart. Even so, their motion during the encounter remains smooth. Gravity bends their trajectories, altering their direction as they swing past the Sun, but it does not introduce sudden deviations. The path is still continuous and describable, using established gravitational models. Astronomers express these motions using parameters that summarize the shape and orientation of the trajectory. One such parameter indicates whether the path is closed or open. Another describes how close the object will come to the Sun. Others specify the tilt of the path, relative to the plane in which the planets orbit. Together, these values allow astronomers to predict positions at any given time, provided no additional forces are at work. In the outer solar system, additional forces are usually negligible. Sunlight is weak, and heating is minimal. For comets, this means that frozen gases remain solid. Without gas escaping from the surface, there is no thrust to alter the motion. The object behaves like a simple mass responding to gravity alone. This assumption underlies early predictions and generally holds well until the object approaches closer to the Sun. Historical observations reinforce this expectation. Many long-period comets have been tracked from large distances inward, their paths matching gravitational predictions closely. Deviations, when present, tend to appear later, after the comet has brightened and developed a visible coma. At that point, gas and dust escaping from the surface can produce small accelerations. These accelerations are typically modest and follow patterns that correlate with distance from the Sun and observed activity. For interstellar objects, the expectation is even simpler at large distances. Without prior heating by the Sun and arriving at high speed, they are assumed to be inert until closer approach. Their motion far out is treated as purely gravitational. Any non-gravitational effects are expected to be too small to detect until the object reaches regions where sunlight can drive physical change. Because of this, early tracking focuses on fitting the data to gravitational models and assessing how well the observations align. Residuals are examined, but small mismatches are often attributed to measurement uncertainty. Only when discrepancies persist across many observations do astronomers consider alternative explanations. The threshold for such consideration is high, because the models have been tested extensively across a wide range of objects and conditions. Expected paths also incorporate the influence of planets, though at great distances these effects are subtle. Massive planets such as Jupiter can alter trajectories significantly during close approaches, but when an object is far away, planetary pulls act as small perturbations layered on top of the Sun's dominant influence. These perturbations are included in calculations to improve accuracy, but they do not change the overall character of the path. The expected behavior of brightness also ties into path predictions. As an object approaches the Sun, its distance from Earth and the Sun changes, affecting how bright it appears. Even without any intrinsic change, reflected sunlight increases as distance decreases. This predictable brightening follows mathematical relationships tied to geometry. Deviations from this pattern can signal physical activity, but at large distances, brightness changes are expected to be slow and smooth. Orientation and rotation are additional considerations, though they are usually secondary early on. A rotating object presents different surface areas to the sun over time, which can modulate heating once activity begins. In the outer solar system, however, the low level of sunlight means rotation has little effect on motion. It may influence brightness slightly, but it does not alter the expected gravitational path. These established expectations form the backdrop against which any new object is assessed. When 3I/Atlas is tracked in the outer regions, its motion is compared against this framework. Astronomers ask whether the data fit within the range of behaviors seen before. They examine whether any apparent deviations can be explained by uncertainties, by incomplete data, or by known influences such as planetary gravity. The language used at this stage remains cautious. Predictions are updated as new measurements arrive. The models are adjusted within their accepted limits. No new forces are assumed without necessity. This restraint reflects both scientific discipline and experience. Many apparent anomalies in early data resolve themselves as observations accumulate. The expected path, then, is not a rigid line, but a corridor of possibilities, constrained by physics and observation. An object may occupy different positions within this corridor as measurements improve. Only when it moves persistently outside this corridor does the question of unexpected behavior arise. In the outer solar system, that threshold is rarely crossed because the environment is stable and the physics is well understood. Within this context, 3I/Atlas continues to be treated as another incoming body whose motion should conform to known patterns. Its early trajectory is assessed in terms of these expectations, establishing what normal behavior looks like before any claim of deviation can be evaluated. The focus remains on defining the standard against which later measurements will be judged, staying firmly within the outermost region of analysis where gravity alone is expected to rule. As observations of 3I/Atlas accumulate, attention turns from broad expectations to the specifics of measured data. Each recorded position is time-stamped and corrected for known effects such as Earth's motion around the Sun and the finite speed of light. These corrections ensure that the object's apparent location reflects its true position in space at the moment the light was emitted. The resulting data set consists of a series of points tracing the object's path against the distant star field. The precision of these measurements depends on several factors. The brightness of the object affects how well its position can be determined. A faint source produces a diffuse signal on the detector, making the exact center harder to locate. Atmospheric conditions blur images taken from the ground, even with correction techniques applied. Instrument calibration, including knowledge of pixel scale and optical distortion, also plays a role. Each source of error contributes to the overall uncertainty associated with a given measurement. To make sense of the data, astronomers fit the observed positions to a model trajectory. This fitting process seeks the path that best matches the measurements given their uncertainties. The quality of the fit is assessed using statistical methods that quantify how closely the model reproduces the observed positions. Residuals, the differences between predicted and observed locations, are examined for patterns. Random scatter suggests noise, while systematic trends indicate that the model may be missing something. For 3I/Atlas, the initial fits appear reasonable. The model based on gravitational forces alone reproduces the observations within expected limits, at least at first. As more data are added, the fit is refined and the predicted future positions are updated. The object remains far from the Sun, and its motion is slow enough that changes from night to night are small. This slow motion places high demands on precision, because even tiny errors can accumulate over time. As the observational arc extends, subtle trends in the residuals become more apparent. The deviations are small, often within the stated uncertainties of individual measurements. However, they persist across different nights and different observatories. This persistence draws attention, not because the deviations are large, but because they are consistent. A consistent offset suggests a real effect rather than random noise. Astronomers respond by checking for mundane explanations. They review the calibration of instruments, reprocess images, and verify reference star catalogs. They examine whether timing errors or coordinate transformations could account for the pattern. Independent data sets are compared to ensure that the trend is not tied to a single telescope or reduction pipeline. This process can take time, as it requires careful cross-checking and sometimes the acquisition of additional data. At the same time, alternative gravitational influences are reassessed. The positions and masses of planets are well known, but their contributions are recalculated to ensure accuracy. Effects from large asteroids or distant massive bodies are considered, though these are typically negligible at the distances involved. The gravitational model is tested and retested because it forms the baseline against which any anomaly is measured. Brightness measurements are also examined alongside positional data. Although the object appears point-like, small changes in brightness can affect centroiding, the process of determining the center of the light distribution. If the object's brightness varies even slightly, it can introduce small positional shifts. By comparing brightness and position over time, astronomers assess whether such effects could produce the observed residuals. During this phase, the language used remains technical and restrained. Rather than declaring a deviation, astronomers describe trends and residuals. They quantify uncertainties and note correlations. The emphasis is on careful description rather than interpretation. The outer solar system context still applies, and the object is assumed to be inert unless evidence suggests otherwise. As data continue to accumulate, the residuals do not disappear. Instead, they show a pattern that suggests a small, continuous acceleration not accounted for by gravity alone. The magnitude of this acceleration is tiny, far smaller than the pull of the Sun, but it is detectable because of the precision of modern astrometry. Importantly, the direction of the inferred acceleration appears roughly aligned with the object's motion rather than pointing toward a specific massive body. This observation is handled cautiously. Small accelerations can arise from subtle effects, including biases in measurement or unmodeled forces. The possibility of an interstellar origin is revisited, as such objects may have higher speeds and different physical properties. However, the models used already account for initial speed and direction, and these factors alone do not explain a continuing deviation. At this stage, the focus remains on the trajectory itself. The question is not yet why the object behaves this way, but whether the behavior is real. Statistical tests are applied to assess the significance of the trend. Confidence grows as the pattern persists across an increasing number of data points. The acceleration remains small but measurable, and it appears to be present even when the object is still far from the Sun. The measured trajectory then begins to diverge slightly from the expected gravitational path. The divergence is gradual, not abrupt. Over time, it accumulates, leading to predicted positions that differ measurably from those based on gravity alone. This divergence is not large enough to change the broad classification of the orbit, but it is sufficient to warrant attention. Throughout this process, care is taken to remain within the bounds of the data. No assumptions are made about physical mechanisms at this stage. The trajectory is described in terms of what is measured and how it compares to models. The outer region of analysis is still in focus, dealing with motion through space rather than physical change. The measured data now define a problem to be addressed, setting the stage for deeper examination while remaining anchored in observation rather than explanation. With a growing body of positional data in hand, attention shifts to how the measured path compares in detail to predictions based on gravity alone. The process is incremental. Each new observation is added, the trajectory recalculated, and the differences examined again. In a purely gravitational case, these differences should shrink as uncertainties decrease. Instead, for 3I/Atlas, the differences persist and evolve in a consistent direction. The deviation does not appear as a sudden change. There is no sharp bend or discontinuity in the path. Rather, the object seems to drift gradually away from where the gravitational model places it. This drift is subtle, at first detectable only through statistical analysis of many measurements. Over time, however, the cumulative effect becomes harder to ignore. Predicted positions based on earlier data no longer align as closely with later observations as expected. The scale of the deviation is small in absolute terms. It amounts to distances that are tiny compared to the overall span of the orbit. Yet astrometry operates at a level where such small differences matter. Modern surveys can measure positions with precision measured in fractions of an arcsecond, allowing minute accelerations to be inferred. When an effect is consistently present across many nights and instruments, its small size does not diminish its significance. To characterize the deviation, astronomers introduce an additional term into the motion model. This term represents a constant or slowly varying acceleration that is not directed toward the Sun in the same way as gravity. When this term is included, the fit to the data improves noticeably. Residuals become smaller and more randomly distributed, indicating that the modified model captures something real about the object's motion. The direction of the inferred acceleration is examined carefully. If it pointed toward the Sun, it might suggest an error in the assumed solar mass or in the distance scale. If it pointed toward a planet, it might indicate an unaccounted gravitational influence. For 3I/Atlas, the direction appears more closely aligned with the object's velocity roughly along its path of travel. This alignment reduces the likelihood that the effect arises from a missing massive body. Timing is also important. The deviation is present while the object remains far from the Sun, where temperatures are low and solar heating is weak. At such distances, native comets typically show little or no activity. Their paths are well described by gravity alone. The presence of a measurable non-gravitational acceleration in this region is unusual, though not entirely without precedent. Astronomers review historical cases to provide context. Some comets have exhibited small deviations at relatively large distances, later attributed to the release of very volatile substances. These substances can sublimate, meaning transition directly from solid to gas at lower temperatures than water ice. Carbon monoxide and carbon dioxide are examples. When such gases escape, they can produce a gentle thrust. However, these effects are usually detected closer to the Sun than where 3I/Atlas currently is. Another consideration is the object's possible interstellar origin. An interstellar body may have a different composition or structure than typical solar system comets. It may contain materials uncommon in native objects, or it may have experienced heating near another star before arriving. Such history could influence how it responds to even weak sunlight. These possibilities are noted but not assumed, as they require evidence beyond trajectory data. The analysis remains focused on what the numbers indicate. The strength of the inferred acceleration is estimated along with its uncertainty. It is found to be small but statistically significant. The confidence grows as the data set expands. The effect does not vanish when older data are reweighted or when subsets of observations are analyzed independently. This robustness strengthens the case that the deviation is not an artifact of measurement. At the same time, caution is maintained. The models used to infer acceleration rely on assumptions about the object's mass and shape, which are not directly measured. The object is treated as a point mass, but in reality it has an extended structure. Light reflected from a non-spherical body can bias positional measurements slightly, especially if brightness varies with rotation. Such effects are investigated to determine whether they could mimic an acceleration aligned with the direction of motion. Brightness data are revisited with this in mind. Variations are small and gradual, consistent with changing distance and viewing angle rather than strong intrinsic activity. No sudden brightening is observed that would suggest a large outburst of material. This absence of dramatic photometric change makes explanations involving strong jets less likely, at least at this stage. The deviation is also compared against expectations for radiation pressure, the force exerted by sunlight itself. Radiation pressure acts on small particles and can alter their motion. For a solid body of typical size, this force is negligible compared to gravity. Only for extremely low density or highly reflective objects would radiation pressure have a measurable effect. Without evidence for such unusual properties, radiation pressure alone does not provide a satisfactory explanation. Throughout this examination, the language remains descriptive rather than interpretive. The deviation is documented, quantified, and tested against alternative models. The aim is to establish its reality and characterize its properties without yet committing to a physical cause. This approach reflects standard practice when confronted with unexpected behavior. By the end of this phase, the conclusion is narrow and specific. The path of 3I/Atlas does not match exactly what is predicted by gravity alone. The mismatch is small, continuous, and aligned roughly with the object's motion. It is detectable while the object remains far from the sun. These statements describe what is observed, not why it occurs. The analysis remains anchored in the outer region of the problem. The focus is still on motion through space, rather than on the object's physical nature. The deviation marks a transition point, where simple expectations no longer fully account for the data. From here, deeper layers of explanation will be considered, but only after the observational foundation has been firmly established and the deviation itself accepted as a real feature of the trajectory. Before any physical explanation is considered, the reliability of the measurements themselves must be examined in detail. Instrument precision sets the boundary between real effects and artifacts. In astrometry, this boundary is defined by how accurately a telescope and its detectors can locate a point of light on the sky night after night under varying conditions. Even small imperfections can introduce biases that resemble true motion. Every observation begins with photons reaching a detector after passing through Earth's atmosphere. Turbulence in the air blurs the image, spreading the light over several pixels. This effect, known as seeing, varies from moment to moment and from site to site. While statistical techniques can mitigate its impact, seeing imposes a fundamental limit on positional accuracy for ground-based observations. For faint objects like 3I/Atlas, the challenge is greater because the signal is weak relative to the background. Detectors themselves introduce additional sources of uncertainty. Each pixel has a finite size and sensitivity. Variations in pixel response, electronic noise, and imperfections in the detector surface can affect how light is recorded. Calibration procedures are designed to correct for these issues using flat field images and bias frames. These corrections reduce systematic errors, but do not eliminate them entirely. Residual effects can shift measured positions by small amounts. Optical systems also contribute. Telescopes distort images slightly, especially toward the edges of the field of view. This distortion is mapped and corrected using reference stars with well-known positions. The accuracy of this correction depends on the quality of the reference catalog and the stability of the optical system. Modern star catalogs are highly precise, but small errors remain, particularly for faint stars or in crowded fields. Timing accuracy is another consideration. Each observation is associated with a precise time because the object is moving. An error of even a fraction of a second can translate into a positional error, especially for faster-moving objects. Observatory clocks are synchronized using standard systems, but delays in data acquisition and processing must be accounted for. These factors are reviewed to ensure consistency across data sets. For 3I/Atlas observations come from multiple observatories using different instruments. This diversity is valuable because it reduces the likelihood that a single systematic issue affects all data. However, it also introduces complexity. Each instrument has its own characteristics, calibration procedures, and error profiles. Combining data requires careful weighting to ensure that measurements with larger uncertainties do not unduly influence the result. Astronomers examine the residuals for correlations with observing conditions. They ask whether deviations are larger when the object is faintest, when it is observed at low elevation above the horizon, or when the background star field is dense. Such correlations can indicate measurement artifacts. For 3I/Atlas, these checks are applied methodically. The deviation persists even when subsets of data taken under the best conditions are considered separately. Another potential source of error is the treatment of the object as a point source. If the object has an extended structure, even one too small to resolve the center of light may not coincide exactly with the center of mass. Changes in brightness distribution across the object could shift the measured position slightly. This effect, known as photocenter shift, can mimic acceleration if it changes systematically over time. To assess this possibility, astronomers analyze images for any sign of elongation or asymmetry. At the distances involved, 3I/Atlas remains unresolved. Its image is consistent with that of a point source convolved with atmospheric seeing. Brightness profiles match those of nearby stars of similar brightness. This similarity suggests that photocenter shifts are minimal, though they cannot be ruled out entirely at very small levels. Statistical methods play a central role in evaluating instrument precision. Each measurement is assigned an uncertainty based on known error sources. When fitting a trajectory, these uncertainties determine how much weight each point carries. If uncertainties are underestimated, the fit will appear worse than it truly is. If they are overestimated, real effects may be masked. Astronomers revisit uncertainty estimates to ensure they are realistic. Reweighting the data is a common test. By increasing the assumed uncertainties, one can see whether the inferred acceleration remains significant. For 3I/Atlas, reasonable adjustments to uncertainty estimates do not eliminate the deviation. The effect weakens slightly, but does not disappear, indicating that it is not solely a consequence of underestimated errors. Another check involves excluding early or late observations to see whether the trend depends on a particular segment of the data. If the deviation arises from a small number of problematic measurements, removing them should reduce or eliminate it. When this test is applied, the deviation remains detectable across multiple subsets, suggesting that it is distributed throughout the data rather than localized. Cross-comparison between observatories provides further insight. If one instrument consistently reports positions offset in a particular direction, that pattern would point to a systematic bias. Instead, the residuals from different observatories show similar behavior. This consistency across independent systems strengthens confidence that the effect is not instrumental. The possibility of catalog errors is also considered. Astrometry relies on reference stars whose positions and motions are catalogued. Errors in these catalogs can propagate into object positions. Modern catalogs incorporate data from space-based missions, and are highly accurate, but they are not perfect. Systematic errors at very small levels can exist. However, such errors would affect many objects in the same region of sky, not just one. No comparable deviations are reported for other objects observed in the same fields. Atmospheric refraction. The bending of light as it passes through the atmosphere is corrected using models that depend on temperature, pressure, and humidity. Imperfect knowledge of these parameters can introduce small positional shifts, especially at low elevations. Observations of 3I/Atlas are examined for sensitivity to elevation. The deviation does not correlate strongly with this factor, reducing the likelihood that refraction errors are responsible. After these checks, the limits of instrument precision are better defined. The combined uncertainties from all known sources are quantified. Within these limits, the deviation remains detectable. This does not imply absolute certainty, but it establishes that the effect lies near or beyond the edge of what can be explained by measurement error alone. The careful examination of instrument precision serves a specific purpose. It narrows the range of plausible explanations by ruling out common sources of error. This process does not explain the deviation, but it clarifies that the data quality is sufficient to justify further analysis. The outer region of inquiry focused on observation and measurement is thus exhausted as fully as possible. At this point, the trajectory of 3I/Atlas stands as a well-measured path with a small, persistent deviation from gravitational expectations. The instruments, while imperfect, appear capable of detecting such an effect. The deviations survive scrutiny from multiple angles, remaining present after systematic errors are considered and constrained. The observational foundation is now firm enough to support a shift in focus from how the data are obtained to what physical influences might account for the measured motion without yet leaving the outer observational frame. With observational and instrumental uncertainties, constrain the next layer of analysis reviews, known gravitational influences in detail. Gravity is the dominant force shaping motion in the solar system, and any unexplained deviation must first be tested against all recognized sources of gravitational pull. This review proceeds systematically, starting with the most obvious contributors and moving outward to more subtle effects. The Sun accounts for the vast majority of gravitational influence on any object passing through the solar system. Its mass is known with high precision, determined through centuries of planetary motion measurements and refined by spacecraft tracking. Small uncertainties in the solar mass would affect the motion of all planets and small bodies in a consistent way. Such uncertainties would not selectively alter the path of a single object. For this reason, the solar contribution is considered secure, and adjustments to it do not resolve the observed deviation. The planets provide the next most significant gravitational influences. Their positions and masses are tracked continuously, with modern ephemerides incorporating data from radar ranging and spacecraft encounters. Jupiter, the most massive planet, can produce large perturbations during close approaches. Saturn, Uranus, and Neptune also contribute measurable effects under certain geometries. For 3I/Atlas, the object remains far from any close planetary encounter during the period of interest. Planetary pulls are included in trajectory calculations, but their magnitudes are small and well characterized. To ensure completeness, the timing and geometry of planetary positions are reviewed carefully. Small bodies can experience cumulative effects from distant planetary pulls over long periods, but these effects are predictable and smooth. They do not produce a steady acceleration aligned with the object's direction of motion unless a close approach is involved. No such approach is present in the relevant interval. Beyond the major planets, the gravitational influence of large asteroids is considered. A small number of asteroids have sufficient mass to perturb nearby objects. Their orbits and masses are known to a degree that allows their effects to be modeled. For 3I/Atlas, no close passages near massive asteroids occur during the observed span. Including these bodies in the calculations produces no meaningful change in the inferred deviation. The collective mass of the asteroid belt and the distant Kuiper belt is another potential contributor. While these regions contain substantial total mass, it is distributed over a wide volume. The net gravitational effect on a passing object is smooth and symmetric. Models that approximate this distributed mass show that its influence is extremely small compared to the Sun and does not produce directional accelerations of the observed type. Attention then turns to more speculative gravitational sources, such as unseen massive bodies. Hypotheses involving distant planets or compact objects are sometimes invoked to explain anomalies. However, such bodies would exert forces that depend on position and direction relative to them. Their influence would likely affect multiple objects in similar regions of space. No corresponding anomalies are reported for other small bodies observed in nearby trajectories, making this explanation unlikely in this context. General relativistic corrections are also reviewed. For objects moving near the Sun or at high speeds, relativistic effects can produce small deviations from Newtonian predictions. These effects are well understood and included in high-precision models. At the distances involved for 3I/Atlas, relativistic contributions are negligible. They do not account for the magnitude or direction of the observed acceleration. Tidal forces from the galaxy itself represent another background influence. The solar system moves through the Milky Way, experiencing weak tidal effects from the galactic gravitational field. These tides shape the distant reservoirs of comets over very long time scales. However, on the scale of months or years, their effect on a single object's trajectory is vanishingly small. They cannot explain a measurable deviation over the observed interval. Gravitational interactions with passing stars are considered as well. In rare cases, a star passing close to the solar system can perturb distant objects. Such encounters are known from stellar motion surveys and are incorporated into models when relevant. No close stellar passage occurs near the path of 3I/Atlas during the period of observation. The influence of distant stars remains too weak to matter on the timescale of interest. The possibility of errors in the assumed distance to the object is also examined. Distance affects how gravitational forces translate into observed motion. If the distance were significantly misestimated, the inferred trajectory could appear to deviate. Distance estimates are derived from the object's motion itself using parallax and orbital fitting. While uncertainties exist, They are not large enough to produce the observed pattern without contradicting other aspects of the data. Throughout this review, the gravitational model is stress-tested. Terms are added and removed, parameters adjusted within their uncertainties, and alternative formulations explored. None of these adjustments remove the need for a small additional acceleration aligned with the object's motion. Gravity, as currently understood and modeled, accounts for most, but not all of the observed behavior. This conclusion is not taken lightly. Gravity is one of the most thoroughly tested aspects of physics, especially within the solar system. Any claim that gravity behaves differently would require extraordinary evidence. In this case, the evidence does not point to a failure of gravitational theory. Instead, it suggests that another force, small but persistent, is acting alongside gravity. The review of gravitational influences thus serves to narrow the field of explanation. By accounting for all known gravitational sources and finding them insufficient, the analysis opens the door to non-gravitational effects. This transition does not imply novelty or mystery. Non-gravitational forces are known to affect small bodies under certain conditions. The task is to determine whether such forces are plausible in this case, and if so, which ones. At the end of this stage, the motion of 3I/Atlas is understood as the sum of a dominant gravitational trajectory and a minor additional component that cannot be attributed to known gravitational influences. This understanding remains descriptive rather than explanatory. It defines what gravity can and cannot account for, establishing a boundary that marks the shift from purely dynamical considerations to the physical properties of the object itself, while still remaining within a careful and methodical framework. Once gravitational explanations are exhausted, attention turns to forces that arise from the object itself rather than from external masses. These are known as non-gravitational forces, a term that refers not to exotic physics, but to small accelerations produced by physical processes acting on or within the body. For small objects in space, such forces are usually weak, but over time they can alter motion in measurable ways. The most common source of non-gravitational acceleration in small solar system bodies is the release of material from the surface. When a solid substance transitions directly into gas, it expands and escapes, carrying momentum with it. The remaining body experiences an equal and opposite reaction, producing a gentle thrust. This process is familiar from comets, which develop comae and tails as they approach the Sun. The effect on motion is typically small but detectable, especially when measured with modern precision. At large distances from the Sun, this process is expected to be minimal. Sunlight is weak and temperatures remain low. Water ice, the most abundant volatile in many comets, remains solid until much closer to the Sun. However, other substances can sublimate at lower temperatures. Carbon monoxide and carbon dioxide are examples of such supervolatile materials. If present near the surface, they can begin to escape even when the object is far out. The presence of these materials is not uniform across all small bodies. Some comets show activity at large distances, while others remain inert until much later. The difference depends on composition structure and thermal history. An object that has spent most of its existence in deep cold may retain near-surface deposits of supervolatile ice. An object that has been heated repeatedly may have lost them long ago. For 3I/Atlas, the inferred acceleration aligns roughly with the direction of motion. This alignment is consistent with outgassing that is not symmetric around the surface. If material escapes preferentially from regions oriented along the direction of travel, the resulting thrust would act in that direction. Such asymmetry can arise from uneven distribution of volatiles, or from the geometry of sunlight exposure combined with rotation. At this stage, the analysis does not assume that outgassing is occurring, but it considers whether such a process could plausibly account for the observed acceleration. The magnitude of the inferred force is compared with what is known from other objects. It is found to be within the range produced by weak outgassing far smaller than the forces seen in highly active comets near the Sun. This comparison suggests that in principle, a modest level of material release could explain the deviation. Another non-gravitational force is radiation pressure, the direct push of sunlight on a surface. This force depends on the area exposed to the reflectivity of the surface and the mass of the object. For dust particles, radiation pressure can be significant, pushing them away from the sun and shaping comet tails. For solid bodies of typical size and density, the effect is usually negligible compared to gravity. To evaluate radiation pressure for 3I/Atlas, assumptions must be made about its size and mass. These properties are not directly measured at this distance, but estimates can be derived from brightness and plausible albedo values. Under reasonable assumptions, radiation pressure alone appears too weak to produce the observed acceleration, unless the object has an unusually low density or extreme reflectivity. Without independent evidence for such properties, radiation pressure is considered a less likely primary cause. Thermal forces provide another possibility. When sunlight heats a rotating body, the warm surface re-emits energy as infrared radiation. This re-emission carries momentum, producing a tiny thrust. Over long periods, this effect can alter the rotation and orbit of small bodies. The magnitude of this force depends on size, shape, rotation rate, and thermal properties. It is well documented for small asteroids, but is generally very small. At large distances from the Sun, thermal effects are expected to be weak, because heating is minimal. For 3I/Atlas, the distance at which the deviation is detected suggests that thermal re-emission would be extremely small. While not entirely negligible in principle, it is unlikely to dominate the observed acceleration under standard assumptions. The possibility of multiple non-gravitational forces acting together is also considered. Weak outgassing combined with radiation pressure or thermal effects could produce a net acceleration aligned with the direction of motion. Such combinations complicate modeling as they require assumptions about physical properties that are not directly observed. The analysis, therefore, remains conservative, focusing on whether any known non-gravitational mechanism could plausibly account for the data. A key constraint comes from the absence of obvious activity. At the distances considered, 3I/Atlas does not display a visible coma or tail. Its brightness changes smoothly, consistent with distance effects rather than sudden releases of material. This absence does not rule out weak outgassing, as gas release can occur at levels below detection thresholds. It does, however, limit the strength and nature of any such process. Comparisons with other objects provide context. Some comets have shown measurable non-gravitational accelerations before developing visible coma. In these cases, sensitive measurements revealed subtle effects that were later confirmed as activity increased. Other objects have exhibited non-gravitational motion without strong visual signatures attributed to low-level gas release or unusual surface properties. The interstellar possibility remains part of the discussion. An object formed around another star may contain materials uncommon in native solar system bodies. It may also have experienced different thermal histories, affecting how volatiles are distributed. Such differences could make it responsive to weak sunlight in ways that are less familiar. These considerations are noted without being adopted as explanations, because they depend on properties not yet established. Modeling non-gravitational forces involves fitting additional parameters to the trajectory. These parameters represent the strength and direction of the force as functions of distance from the Sun. When such models are applied to the data, they can reproduce the observed path with improved accuracy. The parameters required are modest, consistent with gentle forces rather than extreme activity. The improvement in fit does not prove the physical cause, but it demonstrates that the deviation can be described within known physical frameworks. This distinction is important. The analysis does not claim that a particular mechanism is active, only that the motion does not require new physics. Known processes operating at low levels are sufficient in principle. At the end of this stage, the focus remains on motion rather than material detail. Non-gravitational forces are introduced as a category of explanation grounded in established physics. The data suggest that such forces may be at work, but they do not uniquely identify which one dominates. The outer to inner progression continues moving from abstract forces toward the physical characteristics of the object's surface and environment, without yet asserting conclusions or interpretations. With non-gravitational forces identified as a plausible category, the analysis moves inward toward the physical conditions that would allow such forces to operate. The environment surrounding 3I/Atlas is defined first by distance from the Sun, which sets the available energy. At these large distances, sunlight arrives weakly spread thin across space. The amount of energy received per unit area is only a small fraction of what reaches the inner planets. This constraint shapes every physical process on the surface of a small body. Surface temperature follows from this limited energy input. In the outer solar system, equilibrium temperatures are low, often well below the freezing point of water ice. Under these conditions, water remains solid and inactive. Its vapor pressure a measure of how readily it escapes, as gas is extremely small. As a result, water-driven activity is not expected at these distances. Any process involving water ice can be set aside for the moment. Other substances behave differently. Certain gases condense into solid form only at very low temperatures. Carbon monoxide, carbon dioxide, nitrogen, and molecular oxygen are examples. These materials can sublimate at temperatures far below those required for water. Even weak sunlight can provide enough energy to release small amounts of gas if these materials are present near the surface. The rate of release depends on temperature, surface composition, and how deeply the ice is buried. The thermal structure of a small body is layered. The surface responds most quickly to changes in sunlight, warming during exposure and cooling when shaded. Beneath the surface, temperatures change more slowly, buffered by the insulating properties of the material. This creates a gradient with the coldest regions deep below. The depth to which heat penetrates depends on thermal conductivity, density, and rotation rate. For porous, dusty material, heat penetration is shallow, leaving deeper layers largely unaffected by surface conditions. If supervolatile ice is present near or at the surface, even a small increase in temperature can trigger sublimation. The escaping gas must find a path through overlying material. In a porous structure, this path may be diffuse, allowing gas to seep out gently, rather than erupting violently. Such gentle release can persist over long periods, producing a steady, low-level thrust without creating a dense coma. The orientation of the surface relative to the sun also matters. Sunlight does not strike all areas equally. Regions facing the sun receive more energy while others remain in shadow. As the object rotates, different areas are exposed. If rotation is slow or if the axis is tilted, certain regions may experience prolonged illumination. This uneven heating can lead to localized activity, with gas escaping preferentially from specific areas. The rotation state of 3I/Atlas is not directly measured at this stage. Its brightness variations are small, suggesting either a nearly spherical shape, a uniform surface, or a rotation that averages out differences over time. Without clear periodic brightness, changes, rotation rate, and axis orientation remain uncertain. Despite this uncertainty, uneven heating remains a plausible condition, as even subtle differences can matter at low energy levels. Surface composition plays a critical role. A layer of inert material, sometimes called a mantle, can cover volatile, rich layers beneath. This mantle can inhibit gas escape, delaying activity until the object approaches closer to the sun. Alternatively, fractures, pores, or thin spots in the mantle can allow gas to escape at large distances. The presence and properties of such layers depend on the object's history, including past heating and collisions. For an object arriving from interstellar space, the surface history may differ from that of native solar system bodies. It may have experienced different radiation environments, temperatures, and chemical conditions. These factors could influence how volatiles are distributed and how easily they escape. While this possibility is acknowledged, the analysis remains grounded in general physical principles that apply regardless of origin. Thermal modeling provides a way to estimate whether observed accelerations are compatible with plausible gas release rates. By combining estimates of surface temperature, volatile sublimation rates, and object mass, astronomers can calculate the thrust produced by outgassing. For 3I/Atlas, such models indicate that a small area of active surface releasing supervolatile gas at a low rate could generate the inferred acceleration. Importantly, these models do not require dramatic activity. The amount of material involved can be small, insufficient to produce a visible coma against the background of reflected sunlight. Gas released at low density may disperse quickly, remaining below detection thresholds. Dust entrainment, which produces visible features in active comets, may be minimal or absent if gas flow is weak. The direction of thrust depends on where gas escapes. If release occurs preferentially on the sunward side, the resulting force would be directed roughly away from the sun. If release is tied to the direction of motion, perhaps through the interaction of rotation and illumination, the thrust could align more closely with the trajectory. The latter scenario is more complex, but not excluded by physics. Temperature also varies with distance. As the object moves inward even slightly, the increase in sunlight can raise surface temperatures enough to change sublimation rates. This sensitivity means that small changes in distance can produce noticeable changes in gas release. Monitoring whether the inferred acceleration changes with distance provides a test of thermal-driven models. At the distances considered so far, the environment remains cold and stable compared to the inner solar system. The processes described operate at the margins of detectability. This subtlety aligns with the observed behavior, which is marked by small deviations rather than dramatic changes. The physical environment thus supports the possibility of weak, persistent, non-gravitational forces without contradicting observational constraints. Another factor is the object's size and mass. Smaller objects experience larger accelerations for the same thrust because acceleration scales inversely with mass. If 3I/Atlas is relatively small, even a tiny force could produce a measurable effect. Size estimates derived from brightness depend on assumptions about reflectivity. A darker object must be larger to reflect the same amount of light, while a brighter object can be smaller. Without direct measurement, size remains uncertain within a range. Density adds further uncertainty. A porous, low-density body has less mass for a given size, increasing its responsiveness to thrust. Such structures are common among comets, which are often described as loosely bound aggregates of ice and dust. If 3I/Atlas shares this characteristic, its susceptibility to non-gravitational forces would be enhanced. These considerations draw the analysis closer to the object itself. The focus shifts from abstract forces to concrete physical conditions on and near the surface. While many properties remain uncertain, the range of plausible conditions is constrained by known physics and observation. Within this range, weak outgassing driven by supervolatile ices remains a viable explanation for the measured deviation. The progression inward continues deliberately. The environment and thermal conditions establish what processes are possible. They do not yet determine which process is active. That determination requires further examination of composition structure and potential observational signatures, moving deeper into the object's physical nature while maintaining adherence to measured data and established principles. He is now aware that the recalibration triggered by 3I/Atlas does not remain confined to observatories or modeling rooms. It begins to alter how distance itself is felt within the discipline. The narrator describes a subtle expansion of scale in the scientific imagination. For decades, planetary science has treated interstellar space as a boundary condition, a backdrop through which the solar system moves. With this object, interstellar space becomes an active participant, a medium with texture and history. 3I/Atlas carries within it the imprint of radiation fields, shock fronts, and chemical gradients that exist far beyond the sun's reach. As analysts attempt to decode those imprints, they are forced to confront the fact that their local measurements are sampling a much larger cosmic environment. The object's surface chemistry, inferred from faint spectral features and non-detections, as much as from clear signals, hints at prolonged exposure to energetic particles that slowly alter molecular bonds. This is not dramatic erosion, but patient rewriting, a kind of cosmic weathering that operates over millions of years. The narrator notes that such processes have long been theorized, yet rarely observed directly because solar system bodies are shielded by comparatively benign conditions. 3I/Atlas arrives already transformed. He describes how this realization alters the tone of interpretation. Where once deviations were treated as nuisances to be corrected, they are now read as messages encoded in physics. A small excess acceleration becomes evidence of structure. An absence of expected gas lines becomes evidence of prior loss or transformation. Silence in this context is data. The narrator shifts focus to laboratories on Earth, where experimentalists simulate interstellar conditions using vacuum chambers and radiation sources. These experiments, once peripheral, gain new relevance. Samples of analog materials are bombarded, cooled, warmed, fractured, and measured their responses, compared against the stubborn behavior of the object in space. The connection between laboratory and telescope tightens, closing a loop that had remained abstract. He emphasizes that this loop does not close neatly. Each experiment reveals sensitivities to parameters that are poorly constrained, reminding researchers that extrapolation across vast scales is inherently uncertain. Yet uncertainty here is productive. It defines the edges of plausibility. The narrator moves outward again to survey telescopes, scanning the sky with renewed intent. Detection thresholds are reconsidered, cadence patterns adjusted, follow-up protocols streamlined. The presence of 3I/Atlas reframes rarity. Interstellar visitors are no longer hypothetical outliers, but members of a population whose distribution is still unknown. The narrator describes discussions about selection bias, about how many such objects might pass unseen because they are faint, slow, or compositionally dark. Each missed detection becomes a reminder that absence of evidence is shaped by design choices. This awareness leads to proposals that emphasize breadth over precision, early warning over detailed characterization. The scientific culture subtly shifts from optimizing certainty to maximizing encounter. He then turns to the question of origin, not as a puzzle to be solved definitively, but as a landscape of possibilities. 3I/Atlas could have formed in a disk, rich in carbon compounds, or in a region where volatile depletion occurred early or near a massive star whose radiation stripped surfaces clean. Each scenario implies different stellar neighborhoods, different timescales, different probabilities of survival during ejection. The narrator stresses that these scenarios are not speculative indulgences. They are constrained narratives anchored in known astrophysical processes, yet none can be favored decisively. This multiplicity of origins challenges a long-standing habit of classification. Solar system bodies fit into families shaped by shared history. Interstellar objects resist such grouping. They are singular by default, each one a sample of a different system. The narrator suggests that this singularity encourages a shift from taxonomy to biography. Each object is treated less as a type and more as an individual with a unique past. This is not anthropomorphism, but methodological adaptation. It reflects the reality that small number statistics demand case-by-case attention. He describes conferences where presentations end not with conclusions, but with open questions where applause acknowledges rigor rather than resolution. The mood is not frustration, but careful curiosity. As 3I/Atlas recedes from the sun, its activity, if any, diminishes further. The data stream thins, the signal weakens, and the opportunity window narrows. The narrator observes that this phase is as instructive as the approach. The fading reveals which effects were transient and which persist independent of solar influence. Some deviations relax, others remain hinting at internal properties rather than external forcing. The object's departure underscores a truth that planetary scientists know well, but rarely confront so directly. Observation is ephemeral. Missed chances cannot be recovered. This awareness reinforces the urgency of preparedness for the next arrival. He shifts to a broader reflection on method. Science often advances through controlled repetition, but interstellar visitors do not offer repetition on demand. They require readiness rather than replication. The narrator notes that this changes how confidence is built. Instead of relying on repeated experiments, confidence emerges from coherence across disciplines: dynamics, chemistry, materials, science, stellar astrophysics. When independent lines of reasoning converge, even partially, trust grows. 3I/Atlas becomes a test case for this integrative approach. Its study rewards collaboration and exposes gaps where integration fails. The narrator allows himself a moment of stillness, imagining the object now on its outbound trajectory, carrying away the sun's influence and returning to interstellar space altered, yet intact. It leaves behind not a solved equation, but a changed field. He emphasizes that this change is incremental and reversible. Nothing prevents future data from overturning current interpretations. This provisional quality is central. It preserves openness. The narrator then considers the human dimension, the patience required to work on phenomena that may never fully yield. Careers will span only a fraction of the time between such encounters. Many who contribute to understanding 3I/Atlas will not see the next comparable object, yet their work lays scaffolding for those who will. This intergenerational aspect gives the effort quiet meaning. It situates individual measurements within a continuum of inquiry that extends beyond any single event. In the final passages of the section, the narrator returns to distance now understood, not merely as spatial separation, but as experiential gap. Interstellar space is distant, not because it is far, but because its conditions are unfamiliar. 3I/Atlas narrows that gap slightly, offering a tangible link between stellar systems. It does so without spectacle, without clear answers, simply by behaving as it does. The narrator concludes that the most significant consequence of this object may be the way it teaches restraint. It demonstrates that understanding can deepen without closure, that recalibration can proceed without crisis, and that the cosmos does not owe clarity on human timescales. As the object fades from view, the recalculated assumptions remain quietly integrated into practice, waiting for the next messenger to test them again. Beyond the sun's immediate glare, the space around 3I/Atlas remains sparse and cold, and within this outer environment, any release of material is difficult to separate from the background. The region under consideration is not the interior of the object, but the thin zone where any gas or dust might escape and interact with surrounding space. Observations focus on this envelope because it is here that non-gravitational forces can arise without invoking unseen mass or exotic physics. Telescopes sensitive to visible light infrared wavelengths and radio frequencies monitor the object over extended periods, searching for faint signs of activity. What they find is limited and uneven. There's no persistent bright coma of dust, like those seen around many comets approaching the sun. There is no long, luminous tail extending millions of kilometers. Instead, there are hints that appear briefly, and then fade signals close to the detection threshold, sometimes present in one wavelength band and absent in another. This pattern immediately constrains interpretation. Any gas release must be weak, intermittent, or composed of materials that do not radiate strongly at commonly observed wavelengths. Scientists begin by considering the simplest explanation. Even far from the sun, certain volatile substances can sublimate meaning. They pass directly from solid to gas. Carbon monoxide and carbon dioxide are known to do this at low temperatures. If such substances exist near the surface of 3I/Atlas, they could escape slowly, producing a gentle thrust without a dramatic visual display. Measurements, however, show no strong spectral lines associated with these gases. Upper limits are placed on their production rates, indicating that if they are present, they are released in amounts smaller than many models would predict. This absence is not treated as failure, but as information. It narrows the range of plausible surface compositions. Attention then turns to dust. Dust grains reflect sunlight and can be detected as slight increases in brightness or subtle changes in the object's appearance. Careful analysis of images reveals no extended dust cloud, yet small variations in brightness occur that cannot be fully explained by rotation alone. One explanation is the release of very fine particles small enough to disperse quickly and remain close to the object, avoiding the formation of a visible tail. Such particles would contribute to mass loss and momentum transfer while leaving only a faint signature. The environment through which these particles move is nearly empty, so even a small release can persist long enough to influence motion. The focus remains on what is observed rather than what is expected. Models are adjusted to account for minimal dust, low gas output, and irregular timing. Another mechanism is considered. Some materials can fracture or shed grains due to thermal stress without significant gas production. Even modest temperature changes between illuminated and shadowed regions can induce cracking and brittle surfaces. When fragments detach, they carry momentum away from the body. This process does not require volatile ice and does not produce strong emission lines. It fits within known material behavior, though it is difficult to confirm remotely. Observations of brightness do not contradict this idea, but they also do not confirm it. The data allow the possibility without demanding it. The outer envelope of activity remains ambiguous by nature. Scientists resist the urge to resolve this ambiguity prematurely. Instead, they map the range of activity levels consistent with the measurements. These maps show that even extremely low mass loss rates sustained over long periods can account for the observed deviations in trajectory. This reinforces the idea that dramatic displays are not required to produce measurable effects. Quiet processes can accumulate influence over time. The region around 3I/Atlas is thus understood as a zone of subtle exchange rather than explosive release. The surrounding space responds, gently absorbing particles and molecules that quickly disperse into interplanetary and interstellar backgrounds. The sun's radiation pressure plays a role here, pushing on any dust that is released. Radiation pressure is the force exerted by light itself, small but persistent. For tiny particles, this force can be comparable to gravitational attraction. Calculations show that if fine dust is emitted preferentially from certain regions of the surface, radiation pressure could amplify its effect on the object's motion. Again, this requires no unusual assumptions, only particular conditions. Observations neither confirm nor rule out such directional emission. They do, however, show that any dust must be dominated by small grains, as larger particles would be easier to detect. The discussion then extends to time. Activity is not constant. It appears, if present at all, to vary over weeks or months. This variability could be linked to rotation, where certain surface areas are periodically exposed to sunlight, or to the exhaustion of small reservoirs of material. Monitoring over time reveals no clear periodic pattern, suggesting that the process is either irregular or too weak to stand out against noise. The absence of pattern again serves as constraint. It implies that the object is not undergoing sustained global outgassing like a typical comet. The environment remains one of marginal activity. Scientists compare these findings with laboratory studies and with observations of other small bodies. Within the solar system, some asteroids exhibit low-level mass loss driven by thermal fracture or dehydration of minerals. These cases provide analogs, though none are exact matches. The comparison supports the idea that 3I/Atlas could be active without fitting neatly into existing categories. The surrounding gas and dust environment is then framed as transitional, neither inert nor vigorously active. This framing helps integrate the data without forcing classification. As the object moves farther from the sun, the already weak activity diminishes further. Observations become increasingly challenging. Upper limits replace detections, and the envelope of uncertainty widens. Yet the earlier constraints remain valid. They define what must have been happening when the object was closer, even if direct observation is no longer possible. The focus stays on this outer region, resisting the temptation to infer deeper properties prematurely. Gas and dust emissions are treated as surface phenomena interacting with space governed by temperature, composition, and structure at the boundary. The careful accounting of what is not seen becomes as important as what is. In this way, the study of emissions from 3I/Atlas exemplifies a broader scientific discipline. It relies on patience, on respect for limits, and on the disciplined interpretation of faint signals. The region around the object remains quiet, almost empty to human senses, yet it carries the imprint of processes that subtly shape motion. By documenting these processes without embellishment, scientists prepare to move inward, toward questions of material response and internal structure, with a clearer sense of what the surface environment allows and what it forbids. The region now under consideration lies just beneath the boundary, where gas and dust, if present, separate from the solid body. Attention moves inward from the surrounding envelope to the surface and the shallow layers below it, where temperature changes act directly on material. At these depths, the sun's influence is not dramatic, but persistent, delivered as a slow variation in heat that depends on distance rotation and orientation. 3I/Atlas travels on a path that exposes it to sunlight levels unfamiliar to material shaped around the sun. As it approaches, the increase in energy is gradual, yet even modest warming can have consequences when sustained over time. The surface does not respond as a single uniform shell. Instead, it reacts locally with differences set by composition, texture, and porosity. These properties determine how heat is absorbed, conducted, and released. Scientists begin by estimating surface temperatures using well-established principles of energy balance. Incoming sunlight is partly reflected and partly absorbed. The absorbed portion raises the temperature until thermal radiation carries energy back into space. For a dark surface, temperatures rise higher than for a reflective one. For a porous surface, heat penetrates more slowly, creating steep gradients between illuminated and shadowed regions. Calculations indicate that 3I/Atlas likely experiences temperature swings sufficient to stress many common solids, even without reaching levels associated with melting or boiling. These stresses arise because different materials expand by different amounts when warmed. When adjacent grains or layers respond unevenly, internal forces develop. Over repeated cycles, these forces can weaken bonds. The narrator describes how such thermal fatigue has been studied in laboratory samples and observed on airless bodies within the solar system. Rocks fracture not because of extreme heat, but because of repeated modest change. On a small body with low gravity, fragments that detach are not easily retained. Even a slight push can allow them to drift away. The thermal response is further shaped by rotation. As the object spins, surfaces move in and out of sunlight, creating a rhythm of warming and cooling. If rotation is irregular, or if the axis is tilted, some regions may experience longer periods of illumination. These areas warm more deeply, allowing heat to penetrate below the immediate surface. The depth reached depends on thermal conductivity, a measure of how easily heat moves through a material. Estimates suggest that for loosely bound aggregates, heat may affect only the uppermost layers, leaving the interior cold. This mismatch sets up another source of stress. The surface wants to expand and contract, while the interior resists. Over time, this can lead to cracking parallel to the surface, a process known from studies of regolith on asteroids. 3I/Atlas, having spent most of its existence in the colder interstellar environment, may carry materials that have never experienced such cycles before. Their response could differ from that of solar system bodies that have long adapted to solar heating. The narrator notes that some ices undergo phase changes at temperatures below those required for sublimation. In these transitions, the arrangement of molecules shifts, altering density and mechanical strength. Even without producing gas, such changes can generate internal pressure. If these materials are present near the surface, They may contribute to slow restructuring. Observational data do not directly reveal these processes, but they constrain their scale. Any thermal response must be subtle enough to avoid producing a bright coma or strong spectral signals, yet sufficient to influence motion over months. Models show that this balance is possible. A small fraction of the surface undergoing thermal cracking can release enough material to account for measured accelerations. The narrator emphasizes that these are not speculative inventions, but extensions of known physics applied under unfamiliar conditions. Heat also affects how the surface interacts with radiation pressure. A rough surface emits thermal radiation unevenly, producing a recoil force known as thermal thrust. This effect has been measured on artificial satellites and some asteroids. It arises because emitted photons carry momentum. If emission is anisotropic, meaning stronger in one direction than another, the net effect is a gentle push. The strength of this push depends on temperature distribution and surface properties. For 3I/Atlas, the contribution of thermal thrust is difficult to isolate. It is likely small, but even small forces matter over long times. Calculations suggest that thermal emission alone cannot explain the full deviation observed, yet it may contribute alongside other processes. The narrator keeps these contributions distinct, avoiding overstatement. The thermal environment also influences chemical stability. Some compounds break down when warmed, releasing trapped gases or altering surface reflectivity. Changes in reflectivity feed back into temperature, creating localized hot or cold spots. This feedback does not lead to runaway effects under the observed conditions, but it introduces heterogeneity. The surface becomes a mosaic of responses rather than a uniform plane. Telescopic observations of brightness variations support this picture. The light reflected by the object changes in ways consistent with uneven surfaces rather than smooth ones. These variations are modest, but they align with a thermally structured surface. As 3I/Atlas recedes, temperatures drop again. Cooling does not simply reverse warming. Fractures remain. Surfaces altered by heating do not return to their original state. The thermal history becomes recorded in microstructure. Scientists understand this from studies of meteorites, where thermal metamorphism leaves identifiable signatures. Although no sample of 3I/Atlas exists, the analogy guides interpretation. The narrator stresses that this inward step does not yet touch the deep interior. It remains focused on the zone where sunlight exerts its influence most directly. Within this zone, processes are quiet, cumulative, and largely invisible. They operate without spectacle, yet they shape the object's interaction with gravity and radiation. The data gathered while the object is near the sun provide a snapshot of this response. As distance increases, direct influence wanes, but the effects persist in altered surfaces and released fragments now lost to space. Scientists use this understanding to refine their models, adjusting assumptions about conductivity, albedo, and mechanical strength. Each adjustment is bounded by observation. The thermal response of 3I/Atlas remains constrained by what is seen and what is not. There is no evidence for widespread melting, no sign of vigorous sublimation, and no indication of structural collapse. Instead, there is compatibility with a surface that responds to heat by slow adjustment. The narrator concludes the section by holding this image steady. A small body moves through sunlight, its surface warming and cooling, cracking and shedding, at scales too small to see yet sufficient to matter. This response is neither exotic nor extreme. It fits within known material behavior extended to an interstellar origin. By understanding this thermal layer, scientists prepare to move further inward toward questions of bulk structure and cohesion, carrying with them a clearer picture of how the outer skin of 3I/Atlas interacts with the Sun. The focus now shifts beneath the thermally active surface into the bulk of 3I/Atlas, where direct interaction with sunlight no longer dominates, and where internal structure governs how the object responds as a whole. This region cannot be observed directly. Its properties are inferred through the combined effects seen at larger scales, especially motion rotation and resistance to disruption. Scientists approach this inward step cautiously aware that every inference rests on limited data. The object's trajectory provides one of the strongest constraints. The measured deviation from purely gravitational motion implies that any forces acting on the body are not tearing it apart. Whatever mass loss or recoil occurs, the object remains intact. This immediately places lower bounds on internal cohesion. A loosely bound cloud of fragments would disperse under even weak asymmetric forces. 3I/Atlas does not. It behaves as a single body over the entire observation window. From this, researchers infer that its interior must possess sufficient mechanical strength to transmit stresses across its volume. That strength need not be high by terrestrial standards. Even gentle bonding between grains can be enough in a low-gravity environment. Density estimates further narrow possibilities. While no direct mass measurement exists, size estimates combined with plausible compositions allow ranges to be explored. If the object were extremely dense, its response to small forces would be muted, requiring larger activity to explain the observed acceleration. If it were extremely porous, it might deform or fragment more easily. The observed behavior lies between these extremes. Models that fit the data tend to favor moderate porosity, where void spaces exist but do not dominate. Such structures are common among small bodies formed through gentle accumulation rather than violent collision. The narrator notes that this is consistent with current understanding of how many planetesimals form in protoplanetary disks, including those around other stars. Internal layering is another consideration. If 3I/Atlas formed in an environment with changing conditions, its interior might record those changes as variations in composition or grain size. Layering affects how stresses propagate. A homogeneous interior distributes forces evenly, while layered structures can concentrate stress at boundaries. The lack of observed fragmentation suggests that if layering exists, it does not create critical weaknesses at the scales involved. Rotation offers additional clues. Changes in spin rate can reveal internal coupling. Observations indicate that any change in rotation during the observed period is small. This suggests that internal mass redistribution is limited. The object does not appear to be reshaping itself significantly in response to heating or activity. Its moment of inertia remains stable within observational limits. This stability again points to a coherent interior. Scientists also consider the possibility of internal ice. Even if surface volatiles are depleted, deeper layers could retain frozen compounds. The depth at which such materials remain stable depends on thermal conductivity and history. For 3I/Atlas, the brief exposure to solar heating likely affects only the outer layers. Deeper interiors could remain cold, preserving original materials from its formation environment. If such ices exist, they could contribute to internal pressure when warmed slightly, but only if pathways allow gases to escape. The absence of strong outgassing suggests that either such pathways are limited or that volatile content is low. Both possibilities are consistent with the data. The narrator emphasizes that these are constraints, not conclusions. The interior remains largely unknown, bounded by what must be true for the observed behavior to occur. Comparisons with known solar system objects help contextualize these bounds. Some asteroids exhibit similar densities and strengths, while some cometary nuclei are more fragile. 3I/Atlas does not align perfectly with either group. Its inferred properties place it in an intermediate regime. This reinforces the idea that interstellar objects sample a broader range of formation conditions than those preserved locally. The narrator keeps the discussion grounded in physical necessity rather than narrative appeal. Each inferred property is tied to a measurable effect. The internal structure must allow the object to survive passage near the Sun without disruption. It must transmit small forces into coherent acceleration. It must accommodate surface changes without collapsing. These requirements narrow the range of viable interiors. As the object moves away from the Sun, internal temperatures decrease further. Any thermal stresses introduced during approach become locked in place. Cracks formed near the surface do not propagate deeply unless driven by strong gradients which are absent. The interior remains largely insulated from short-term change. This insulation means that the bulk of 3I/Atlas today is likely similar to what it was before entering the solar system. The narrator notes that this makes the object valuable as a physical archive. Its interior may preserve conditions from another stellar system with minimal alteration, yet this value is abstract. Without samples, preservation can only be inferred. The scientific approach remains restrained. Internal structure is treated as a set of allowable states rather than a single picture. This restraint is deliberate. Overinterpretation would exceed what the data support. The narrator reflects that such caution is not a weakness, but a strength. It ensures that future observations of other interstellar objects can be compared without forcing them into preconceived categories. 3I/Atlas thus contributes indirectly by shaping expectations. It suggests that interstellar bodies can be mechanically robust, moderately porous, and internally coherent, even after long journeys through space. These qualities influence how future surveys are designed and how models are constructed. The inward exploration pauses here at the limit of what can be responsibly inferred. Beyond this point, speculation would replace constraint. The narrator holds the interior as a quiet, largely unchanged core, carrying the weight of the object and transmitting its response to the outside world. This core does not announce itself. It is known only through its effects. By delineating these effects carefully, scientists prepare to move one step further inward toward the role of rotation and orientation in shaping how internal and external forces combine. Attention turns now to rotation and orientation, not as abstract properties, but as active mediators between internal structure and external forces. This region of inquiry sits inward from bulk composition because it concerns how the whole body presents itself to space over time. Rotation determines which surfaces receive sunlight, how thermal stresses accumulate, and how any emitted material translates into net motion. For 3I/Atlas, rotation is not directly visible. It must be inferred from changes in brightness, subtle variations in trajectory, and the stability of observed effects. These inferences are necessarily cautious, yet they offer meaningful constraints. Light curves, which track how reflected sunlight varies with time, provide the primary clue. Observations show modest fluctuations consistent with an irregular shape rotating steadily. There is no evidence for extreme elongation or rapid tumbling. The absence of dramatic brightness swings suggests that the object does not present vastly different cross-sections during rotation. This implies either a relatively compact shape or an orientation that limits variation. Both possibilities influence how forces act. A steady rotation tends to average local effects over time. If heating or material release is confined to small areas, rotation spreads their influence, reducing the likelihood of sudden changes. This averaging is important because the observed non-gravitational acceleration of 3I/Atlas is smooth rather than erratic. The motion does not show abrupt shifts that would signal strong, localized jets switching on and off. Instead, the deviation accumulates gradually, consistent with forces modulated by rotation. Orientation adds another layer. The axis around which the object spins may be tilted relative to its path around the sun. Such tilt affects seasonal exposure, determining which regions receive prolonged illumination. If the axis points toward the sun for part of the trajectory, one hemisphere may experience sustained warming while the other remains cooler. This asymmetry can create a persistent bias in thermal emission or material release. Even if activity is weak, its direction matters. A small thrust applied consistently in one direction can produce a measurable effect over months. Scientists explore a range of plausible orientations to see which align with the data. They find that many configurations can reproduce the observed acceleration, provided the forces are modest and unevenly distributed. This reinforces the conclusion that no extreme assumptions are required. Rotation rate is also considered. If the object spins too slowly, individual regions remain heated or shadowed for long periods, potentially enhancing thermal stress. If it spins too quickly, temperature differences are smoothed out, reducing stress, but increasing the effectiveness of thermal recoil as emission becomes more uniform, yet still directional. The available data suggest a rotation period that lies within common ranges for small bodies neither exceptionally slow nor fast. This middling rotation supports a scenario in which multiple weak effects combine rather than a single dominant mechanism. The narrator emphasizes that rotation does not create new forces, it organizes existing ones. It determines timing, direction, and persistence. In this sense, rotation acts as a translator between surface processes and overall motion. The stability of rotation is equally important. Large changes in spin rate would indicate significant torques, perhaps from strong jets or uneven mass loss. Observations do not show such changes. Any torque acting on 3I/Atlas must therefore be small or balanced over time. This balance can arise naturally if activity occurs in pairs of regions, or if the rotation axis is oriented such that opposing forces partially cancel. The data are consistent with this quiet balance. Orientation relative to Earth also affects interpretation. As the object moves along its trajectory, viewing geometry changes. Some variations in brightness may result from changing angles rather than intrinsic activity. Scientists account for this by modeling how light reflects from different shapes and orientations. After correction, residual variations remain small. This further constrains rotation models favoring simplicity. The narrator notes that simplicity here is not aesthetic, but empirical. More complex rotational states would likely produce signatures that are not observed. The coupling between rotation and internal structure is subtle but significant. A rigid interior supports coherent rotation. A loosely bound interior might damp or alter spin in response to small forces. The apparent stability of rotation thus feeds back into earlier inferences about internal cohesion. It suggests that the object behaves as a single rotating mass, rather than a collection of independently moving parts. This coherence is crucial for interpreting non-gravitational acceleration. Without it, forces applied at the surface would not translate cleanly into overall motion. Rotation also influences how long any given surface feature persists. Fractures, pits, or exposed materials created by thermal stress are carried in and out of sunlight. Their evolution depends on how often they are heated. A stable rotation pattern allows these features to evolve gradually. There's no evidence that the object undergoes chaotic tumbling, which would expose surfaces unpredictably and likely enhance mass loss. The absence of such behavior supports a calm thermal history during observation. As 3I/Atlas moves away from the Sun, rotational effects change subtly. Reduced heating lowers the amplitude of temperature cycles. Any thermal recoil diminishes. If material release occurred, it becomes even weaker. Yet rotation continues, preserving orientation relative to inertial space. This persistence means that any cumulative effects acquired during approach are not undone. The object carries its rotational state forward unchanged by the brief encounter. The narrator reflects on how rotation serves as a bridge between scales. It links microscopic processes like grain expansion and photon emission to macroscopic outcomes like trajectory deviation. This linkage does not require dramatic activity. It relies on consistency. Small effects, when aligned by rotation, become legible in motion. This understanding tempers interpretation. Scientists avoid attributing too much to any single mechanism. Instead, they see rotation as a context that allows multiple weak processes to add coherently. The study of rotation also highlights limits. Without resolved images or in situ measurements, orientation cannot be pinned down uniquely. Multiple rotational states remain possible. The goal is not to select one arbitrarily, but to define the family of states compatible with observation. This family is narrower than it would be without data, yet broad enough to accommodate uncertainty. The narrator stresses that this approach preserves flexibility for future encounters. If another interstellar object exhibits similar behavior, comparisons can refine these rotational constraints. If it behaves differently, models can expand. Rotation in this sense becomes a comparative parameter rather than a fixed label. The inward exploration pauses again at a natural boundary. Beyond rotation lies no deeper physical layer that can be inferred without speculation. What remains is synthesis, not in the sense of drawing conclusions, but in recognizing how the explored regions interact. Rotation integrates surface response, internal structure, and external forces into a coherent whole. By understanding this integration, scientists are better prepared to articulate what remains uncertain and why. 3I/Atlas continues outward, its spin unchanged, its orientation slowly carrying different faces into distant starlight. The forces that once nudged its path fade, but the rotational state endures a quiet record of interaction between a small body and a star it will never meet again. The final region of examination lies not deeper within the object itself, but at the boundary of present knowledge where all previously considered layers meet their limits. This region is defined by uncertainty that cannot yet be resolved by additional observation of 3I/Atlas. It is not an abstract uncertainty, but a structured one shaped by constraints accumulated from motion surface response, internal coherence, and rotation. Scientists gather these constraints and observe how they intersect. What emerges is not a single explanation, but a narrow corridor of allowable behavior. 3I/Atlas must be massive enough to remain intact, structured enough to rotate coherently, responsive enough to exhibit small, non-gravitational forces, and quiet enough to avoid detectable large-scale activity. These requirements exclude many possibilities that might initially seem plausible. They also demonstrate that the object's behavior, while unusual, does not violate known physical laws. Within this corridor, uncertainties persist. One uncertainty concerns composition. Surface observations limit what materials can dominate the outer layers, yet they do not uniquely identify them. Several mixtures of minerals, organics, and depleted volatiles remain consistent with the data. Each mixture implies a different formation environment, but none can be selected decisively. Another uncertainty concerns history. The object's journey through interstellar space likely altered it, but the extent and nature of that alteration are difficult to quantify. Cosmic radiation, micrometeoroid impacts, and thermal cycling near other stars could all have played roles. The present state of 3I/Atlas carries traces of this history, but those traces are blurred by overlapping processes. Scientists acknowledge this blur rather than attempting to sharpen it artificially. The limits of inference are treated as part of the result. A further uncertainty lies in population context. With so few interstellar objects observed, it is unclear whether 3I/Atlas is typical or exceptional. Its behavior may represent a common class that has simply gone undetected until now, or it may occupy a rare corner of parameter space. Current surveys cannot resolve this. Detection biases favor certain sizes, speeds, and brightness levels. Objects that behave differently may pass unnoticed. This uncertainty affects interpretation subtly but persistently. It discourages overgeneralization. Each property inferred for 3I/Atlas is framed as provisional, applicable to this object alone, until further evidence accumulates. The narrator notes that this restraint marks a shift in scientific posture. Rather than seeking to assimilate the object into existing categories, Researchers allow it to remain partially unclassified. This is not a failure of classification, but an acknowledgement of sampling limits. The study of 3I/Atlas becomes a case study rather than a template. Another boundary concerns modeling itself. Physical models are only as good as their inputs, and several key inputs remain poorly constrained. Surface roughness, grain size distribution, internal bonding strength, and exact rotation state all influence outcomes. Models explore ranges rather than points. When multiple models fit the data equally well, none is elevated prematurely. This multiplicity is documented rather than collapsed. It serves as a guide for future observation strategies, indicating which measurements would most effectively reduce uncertainty. The object thus influences not only current understanding, but future priorities. As 3I/Atlas moves farther away, the opportunity for new data closes. Its signal fades below detection thresholds. At this stage, uncertainty no longer shrinks. It stabilizes. What remains is a defined space of possibilities. Scientists archive observations, publish analyses, and compare notes across disciplines. The object transitions from an active target to a reference point. Its role shifts from being observed to being cited in discussions of method, expectation, and preparedness. The narrator emphasizes that this transition is natural and recurrent in science. Objects come and go. Frameworks persist. 3I/Atlas contributes to a gradual adjustment of those frameworks. It reinforces the idea that small bodies can carry subtle histories, that interstellar space is not inert, and that modest forces can matter when acting consistently. These ideas do not overturn existing theory. They refine it. Importantly, they do so without requiring dramatic revision. The recalculation prompted by 3I/Atlas is incremental, distributed across many small assumptions, rather than concentrated in a single revelation. The narrator remains careful to avoid assigning meaning beyond this process. There is no implication that the object is special in intent or purpose. Its significance lies solely in interaction. It behaves according to physical laws, and those laws, when applied carefully, accommodate its behavior. What changes is not the universe, but human understanding of how familiar principles operate under unfamiliar conditions. This understanding remains incomplete. It is expected to remain so until additional interstellar objects are observed and compared. The narrator holds this incompleteness as the natural endpoint of the inward journey. The exploration cannot proceed further without leaving the ground of evidence. By stopping here, science maintains continuity with its own standards. 3I/Atlas continues outward, becoming once again part of the interstellar background. Its passage through the solar system is brief in cosmic terms, yet long enough to leave a trace in data and discourse. That trace does not resolve into a single answer. It resolves into a clarified set of questions and constraints. This resolution is sufficient. It allows the field to move forward without closing itself prematurely. The inward path ends at this boundary, where knowledge meets its limits and remains attentive, waiting not for closure, but for the next opportunity to observe, measure, and refine.